All right, section 6 is solutions by eigenvalues. And so if a real n by n matrix A has an eigenvalue, lambda, with corresponding eigenvector k, then x equals e to the lambda t times k is a solution to the equation x prime equals a times x. And we also have a theorem that says that if a real n by n matrix A is diagonalizable, then A has eigenvalues with n linearly independent eigenvectors. And if the eigenvalues are real, then the general solution to this equation is the linear combination of each of them. So C1 times e to the first eigenvalue, t times the eigenvector, plus C2. So it's this linear combination of all of the e to the eigenvalues and then times the eigenvectors. Do you remember what diagonalizable means? Diagonalizable, what that means is the number of independent eigenvectors is equal to the sum of all the multiplicities of the eigenvalues. All right, so let's do some examples. We're going to find the eigenvalues and eigenvectors of the given matrix A, and then find the general homogeneous solution to this equation. Okay, so let's do it. So example 1 is that matrix A is 1, -3, -2, 2. And remember, to find the eigenvalues, what we did was we took lambda times the identity matrix minus A. Remember that, where lambda was out front. Identity matrix is, this is a 2 by 2, so 1, 0, 0, 1. Remember, you can't just subtract a number from a matrix. You got to put it into matrix form. And so remember that this was lambda 0, 0, lambda, and then minus A. So 1, -3, -2, 2, which ended up giving you that lambda I minus A is, it would be a lambda minus 1, 0 minus -3, so now it's a positive 3. 0 minus -2, so now it's a positive 2, and then lambda minus 2. All right, and then we found the characteristic polynomial by finding the determinant of lambda I minus A. And the determinant is just multiplying, it's a 2 by 2, so just multiply down the diagonal, lambda minus 1 times lambda minus 2, minus multiplying down the other diagonal, which was 3 times 2. All right, so what does this give you? It gives you lambda squared, you FOIL it out, minus 2 lambda minus 1 lambda, so a minus 3 lambda, plus 2, but then minus 6 will leave you with a minus 4. And this factors as lambda minus 4 and lambda plus 1. And so we found that characteristic polynomial, and then setting it equal to 0 will end up setting this equal to 0 and solving for the lambdas will give you eigenvalues of 4 and -1. Then we went and plugged each of these in to this matrix here. So when lambda, I'll call it lambda 1, so the first eigenvalue I've got is 4. Then my matrix would be a 4 minus 1 is 3. This is a 3, that's a 2. And then 4 minus 2 would give you a 2. And we want to know, when is this equal to 0? And if you do about -2 row 1 plus 3 row 2, that'll give you a -6 plus 6 is 0, -6 plus 6 is 0, 0 plus 0 is 0. Yeah, all right, well then that means that this first line means 3x1 plus 3x2 is equal to 0, which then gives you that x2 is equal to -x1. And so what I would do is I would let x1 equal a, and then x2 would equal negative a. And so then that means that your eigenvector for this first eigenvalue of 4 would be a negative a. And then, of course, we always just factored out the a and used 1 and negative 1. Okay, so that's for the first eigenvalue of 4. Now we're going to do the same thing for the second eigenvalue of negative 1. So for the second eigenvalue of negative 1, I'm going to plug it in. Negative 1 minus 1 will give me negative 2. This is a 3. That's a 2. Negative 1 minus 2 gives me negative 3. Now, and it looks like I can just add row 1 to row 2. And that'll give me a 0, a 0, and a 0. And then this guy's still a negative 2 and a 3. All right, so this first line tells me that negative 2x1 plus 3x2 is equal to 0, which means x2 would be 2/3 x1. Yeah, I prefer to not have fractions, so I'm going to let x1 equal 3a, and then that means x2 would equal 2a. Now, then that way I don't have a, you could let x1 be 1, but then your x2 would be 2/3, right? Or let x1 be a. You could have fractions, but I prefer not to. And so that means your second eigenvector is 3a, 2a, and we always factored out the a and just left it with 3 and 2. Yeah. And so our homogeneous solution is the linear combination of, okay, so my first eigenvalue was 4. So I'm going to have a C1 e to the eigenvalue is 4 times t times its eigenvector, which was 1, negative 1, and then plus C2 e to the, this eigenvalue was negative 1, so it'll be to the negative t power times its eigenvalue, which is the eigenvector, which is 3, 2. There's your general homogeneous solution. All right, let's do another example. How about this time if a is 2, 4, negative 2, negative 2? All right, so your lambda I minus a would just be lambda minus 2, a negative 4, a positive 2, and a lambda plus 2. Your characteristic polynomial would be lambda minus 2 times lambda plus 2 minus negative 8, so a plus 8. Well, that gives you that it is, let's go this way, this is lambda squared. The inners will cancel out, right? So a minus 4 and then a plus 8, which will give you lambda squared plus 4. Setting that equal to 0 will give you that lambda squared is equal to negative 4, which means lambda is equal to plus or minus 2i. All right, so start with the first eigenvalue of 2i, and that'll give you I always write my imaginary part second. So it's 2i minus 2, but I'm going to write it as negative 2 plus 2i, just because I always write it in a plus bi form. This is still a negative 4. This is still a 2, and then a positive 2 plus 2i. We want to solve, when are these 0? And so if you just, I mean, you could do stuff to this, but here's what I noticed. I'm going to take this second equation, and what that means is 2x1 plus 2 plus 2i x2 is equal to 0, and which means x1 is going to equal negative 1 plus I times x2. And if you plug that into this first equation, it will satisfy that. Plug it in, right, where it satisfies the first equation also, because it's a -2 plus 2i times x1, which was this -1 plus I x2, right? And then minus 4x2 is equal to 0. And when you multiply this all out, it does satisfy it. So, yeah, because you would go 2, positive 2, a positive 2i, a minus 2i, and then a minus 2i squared. You end up with 4x2. It ends up being a 4x2 minus 4x2, which is equal to 0. So this satisfies both equations. And so if I let x2 equal, since I have a negative here, I'm going to let it equal negative a. Then x1 will equal a 1 plus I times a. Didn't have to do it that way. That's the way I chose to do it. All right, and so then your eigenvector is going to be 1 plus I times a and a negative a, which remember we've usually factored off the a, and then it's a 1 plus I and then a negative 1. All right, and then if you remember that lambda 2 was negative 2i, that's just the conjugate. Okay, because I can spell conjugate, where K2 is just going to be a times the conjugate of these guys. Conjugate would be 1 minus I. This is negative 1 plus 0i, so its conjugate is just 0, 1. But we only need one of them. We didn't need both when it came to the imaginary complex or the complex solutions. So our solution is e times lambda 1t times k1. And so that's just an e to the 2i t times 1 plus I and negative 1. We're not done because we want real solutions. So if you remember, when you've got an e to the imaginary power here, it's like an e to the 0 plus 2i t, yeah, which means that that's equivalent to e to the 0 times cosine of 2t plus I sine of 2t. Yeah, and e to the 0 is just 1. So basically what it comes down to is our solution is cosine of 2t plus I sine of 2t times this matrix 1 plus I and negative 1. And then we'll distribute those, because what we need to find the a. You know how this, if we multiply these through, it'll be a plus bi. We want just the a and just the b. We just want the real parts of those solutions, is what will give us our answer. All right, so I'm going to multiply these out. I'm foiling, okay? Keep in mind, I'm not going to show it out. I'm not going to separate it, but I'm going to multiply cosine of 2t plus I sine of 2t times 1. So I'm going to multiply these guys in. So it's a cosine of 2t plus I sine of 2t. That was times 1. And then I'm also going to multiply this whole thing times I. So that gives me a plus I cosine of 2t plus I squared sine of 2t. That was just the top row. Distributing it in. And then this whole guy times negative 1. All right, that's easy. Negative cosine of 2t minus I sine of 2t. Yeah. Okay, so now what I'm going to do is I'm going to separate these into two separate matrices, one where it's only got the real parts and one where it's got the imaginary part. So this is equivalent to cosine of 2t is a real part. I, that's an imaginary part. I is an imaginary part. I squared, though, is -1. So this ends up being a real. This is minus sine of 2t. And that's because I squared is -1, right? So, okay. So that's the real part. And then plus I times, so I'm separating out to the imaginary part of this. When I factor out an I from here, I would have sine of 2t plus cosine of 2t. Down below, the negative cosine of 2t is real. And then this one has an I on it, so I'll put negative sine of 2t in this matrix there. Yeah. All right, now, here's the deal. This guy is a real solution, and this guy is a real solution. And so our answer is going to be the linear combination of these two real solutions. So my solution is C1 times this matrix of cosine of 2t minus sine of 2t and negative cosine of 2t. And then plus C2 of sine of 2t plus cosine of 2t and negative sine of 2t. And there's your solution. Yes. 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 Okay. Let's do another example. All right. How about a 3 by 3? -3, 0, -3, 1, -2, 3, and 1, 0, 1. All right, so start off with your lambda I minus a, which would be lambda plus 3, 0 minus 0, 0 minus -3. Row 2 would be this. Yeah, right. It would be lambda 0, 0, 0, lambda 0, 0, 0, lambda. And then minus this matrix A. Yeah. All right, so we got 0 minus 1, lambda minus -2, which gives me a lambda plus 2, 0 minus 3. Third row would be 0 minus 1, 0 minus 0, and then lambda minus 1. All right. So we need to find, for our characteristic polynomial, I do it by finding the determinant of this guy. You could do row 1 times these guys, but here's what I noticed. I noticed that column 2 has 2 zeros in it. So I'm going to use column 2. You'll get the same answer if you used row 1. You're just going to have to do more work. So by doing this guy, remember that this would be a plus minus plus. If this is a minus, that makes this a plus and then a minus. So it's really like -0 plus pi or lambda plus 2 times the determinant of, if you're crossing out this and this guy and the middle guy, you would have lambda plus 3 and 3 and -1 and lambda minus 1 is the determinant you're going to find. Just if you've got 2 zeros in a row or a column, it's definitely easier. And then remember the signs in front alternate. So it's positive, negative, positive. If that one's negative, this one's positive, that one's negative. You remember that. Okay. So then that gives me a lambda plus 2 times, all right, this will be a lambda plus 3 times a lambda minus 1 minus -3. And then that becomes a lambda plus 2 times, so it would be lambda squared minus 1 plus 3, so a plus 2 lambda minus 3, but then a plus 3. Nice. Okay, factoring out a lambda out of this guy, since they're in both, I'll have a lambda times a lambda plus 2 times another lambda plus 2. All right, so we got a multiplicity on that guy. All right, so uh, that means that my first guy is 0. My first eigenvalue is 0. Other eigenvalue is -2. It's got a multiplicity of 2, so we got to watch out. Make sure that we get 2 linearly independent eigenvectors from that in order to be able to do this. All right, so first eigenvalue is 0. And when I plug that into this guy, I'll have a 3, 0, 3. -1, 2, -3. -1, 0, -1. And we're solving for when are these equal to 0. All right. I'm going to take this 3 and add it to 3 times row 2 to zero this guy out. So row 1 plus 3 times row 2 will give me a 0. 0 plus 6. 0 or 3 plus -9 will give me a -6 and then a 0. Do the same thing for row 3. Row 1 plus 3 times row 3. 3 minus 3 is 0. 0 plus 0 is still 0. 3 plus -3 is 0. And then 0. You could keep going. I'm going to stop right there. This is enough for me to see what's happening. This first row says 3x1 plus 3x3 is equal to 0, which means that x3 is equal to a negative x1. Second row says 6x2 minus 6x3 is 0, which means x2 is equal to x3. All right, so if I let x1 equal a, well, then that means that x3 would equal negative, and it's equal to negative x1. And since x2 is equal to x3, x2 is also equal to negative a. So my eigenvector corresponding to when your eigenvalue is 0 would be x1 is a, x3 is negative a, which means that it's 1, -1, -1. All right. Now we're going to do the same thing for the second eigenvalue, which was -2, keeping in mind it's got a multiplicity of 2. All right, so plugging in a -2 in there, I would have a 1, 0, 3, -1, -2 plus 2 will give you 0, -3, -1, 0, and -2 minus 1 is a -3. All right, well, if I do row 1 plus row 2, I would get a 0, 0, 0. Whoops, I forgot my 0, 0, 0. Taking row 1 and adding it to row 3, 0, 0. Oh, nice. Okay. And then my first row was a 1, 0, 3, 0. Okay, so what's the relationship there? Well, that first row says x1 plus 3x3 is equal to 0. So that means x1 is equal to -3x3. So if I let x3 equal, how about I let it be a negative a? You could have done a also. There's more than one correct answer on these guys, right? Then x1 would just equal 3 times a. What I usually do is I try to make my x1 a positive. That's just me. All right, and then what about x2? There isn't anything about x2. So x2 could be anything. So don't let it be a. It needs to equal some other value. I'll call it b. So what that means is that your eigenvector is 3a, x2 is b, and x3 is negative a. Yeah, which that means that it's I can rewrite this as A times 3, 0, negative 1 plus B times 0, 1, 0. You got two linearly independent eigenvectors for this guy, which had a multiplicity of 2. So we're golden. All right, so what is our answer then? Your homogeneous solution is C1 e to the, it was an eigenvalue of 0, so 0t times its eigenvector of 1, negative 1, negative 1, plus C2 times e to the negative 2t times the first guy, 3, 0, negative 1, and then plus C3 e to the negative 2t times 0, 1, 0. Here's your answer. Nice, huh? All right. And obviously you don't need to have the e to the 0t, right? Because that's just 1. You could have just had C1 times this guy, which is how I would have done it, but whatever. I don't feel like rewriting the whole thing. Okay, let's do one more example. How about if A is 2, negative 1, 2, and 4? All right. Lambda I minus A would be lambda minus 2, positive 1, negative 2, lambda minus 4. Your characteristic polynomial would be the determinant of this guy. So lambda minus 2 times lambda minus 4 minus a negative 2. Well, that's a lambda squared minus 4 minus 2, so a minus 6 lambda plus 8 plus 2, so a plus 10. All right, we want to factor that. Two numbers that multiply to 10 and add to negative 6, not going to happen. So when we're trying to solve for when is this 0, we want lambda squared minus 6 lambda plus 10 equals 0. You're going to need to complete the square or do quadratic formula. That works too. But whenever this number is an even number, it's so much easier to just complete the square. Subtract that 10 over. Take the negative 6, cut it in half, you'd get negative 3. Squaring that gives you 9. So that means this is lambda minus 3, quantity squared equals negative 1, which will end up giving you with a lambda equals a positive 3 plus or minus I. All right. So those are our two eigenvalues. All right. So let's do 3 plus I. Plugging in a 3 plus I would give you a 3 minus 2. So a 1 plus I here, got a 1, a negative 2. 3 plus I minus 4 would be a negative 1 plus I. We want to solve for when that's 0 and 0. Okay, I'm going to do the same trick I did last time where I'm going to take this first equation here. What it's saying is 1 plus I times x1 plus x2 is equal to 0, which means x2 is going to equal a negative 1 plus I x1. I'll let you confirm it for yourself, but this does satisfy the other equation. If you plug in, no, I'll do it in another color. It would be a negative 2x1 plus a negative 1 plus I times x2, which we said was a negative 1 plus I x1. And that'll equal 0. And it will. Now, when you multiply these two together, it must become a positive 2x1. You can confirm it on your own, but so that means that this is a true relationship, which means that I'm going to let x1 equal a. Yeah, I'm letting it equal positive a just because that's what I like to do. And then x2 would equal a negative 1 plus I times a. So that means your eigenvector for this guy is an a times a negative 1 plus I times a. Factoring out the a will give me a 1 and a negative 1 plus I. Yeah? Okay, now our solution to this guy is e to the lambda t times your eigenvector. So that means that it's e to the 3 plus it times 1 and how about a negative 1 minus I? I'm going to I distributed the negative in there. Yeah. And then remember, e to the 3 plus I t is e to the 3t times cosine of t plus I sine, no, I times e to the 3t times sine of 1t. And we're going to multiply that times 1 and negative 1 minus I. Yeah. All right. So what we're going to do is distribute this into both. So now I've got still a 2 by 1 matrix, but I'm just going to be distributing this. Okay, so top guy is easy because we're just multiplying it times 1. So that's just an e to the 3t cosine of t plus I e to the 3t sine of t. When I do this bottom guy, though, you want to take this and multiply it times negative 1, and then take this and multiply it times negative I. It's foiling also. For me, I'll take the whole thing, multiply it times the first. So that's a times negative 1 would give me a negative e to the 3t cosine of t minus I e to the 3t sine of t. That was this whole thing times the negative 1. Now I'm going to take the whole thing and multiply it times the negative I. So that would be a negative I e to the 3t cosine of t minus I times positive I, so a minus I squared e to the 3t sine of t. Yeah. And then I'm going to split this up into, I'm going to separate it into two matrices, one where I have factored out an I, because you want the a plus bi. A is a solution, b is a solution. So, all right, so that means that this is, all right, on the top row, e to the 3t will go in the real matrix. Then this guy will be in the matrix that has the I factored out. So we got e to the 3t cosine of t, and then, boy, I'm leaving myself enough room here, and then plus I times, and you'd have an e to the 3t sine of t. That on the first row. Second row, anything without an I in it, right? So negative e to the 3t cosine of t is real. Has an I in it, has an I in it. I know that has an I in it, but remember I squared is negative 1. And so you're going minus a negative 1. So that means you'll end up adding e to the 3t sine of t. And then over here, you've got, I factored out this I, so I would have a negative e to the 3t sine of t and a minus e to the 3t cosine of t. Yeah, where this is a real solution, and so is this guy. Yeah. And so your answer is the linear combination of these two real solutions. So your homogeneous solution is C1 times the first matrix. I'm going to write the bottom one first so that way I'm neater. Cosine of t plus e3t sine of t e to the 3t cosine of t. Okay, there's the first guy, plus C2 times negative E3t sine of t minus e to the 3t cosine of t, and the top row is just an e to the 3t sine of t. There's your homogeneous solution. All right. That's it. Hope you guys have a great day. Bye.